Alright, welcome. I'm Petr Šilling, and on behalf of my colleagues Viktor, Malík and Tomas, Vojnar, I'd like to introduce our paper applying custom patterns in semantic equality analysis. I'll start with a brief introduction to our problem domain and to diffcamp, the framework we use. Then I'll explain our proposed pattern matching algorithm, and finally I'll go over our experiments on the Linux kernel. I'd also like to note that this work has been done in cooperation with the Brno University of Technology, Faculty of Information Technology, and with Red Hat. And with that said, let's jump straight into it. So, let's imagine we have a large-scale project, such as the Linux kernel, which requires strict semantic stability of at least some of its core parts. And now this is not something we can guarantee simply by using testing. And while we could use more formal methods for static analysis of semantic equivalence, those do not scale very well, at least not to projects of such size. And this is why we're developing a more scalable framework for automatic semantic equivalence analysis, which I'll introduce in a minute. And in particular in this work, we're trying to alleviate a common issue we found by analyzing projects such as the Linux kernel, and that is that we sometimes see that even semantics altering changes, typically some bug fixes and security fixes, need to be incorporated into even the more stable parts of the code base. And while we could simply disregard this behavior, we can also see that these changes are generally repetitive, and therefore we propose to eliminate them using custom patterns that describe these changes. And now let's look to our framework. We call our framework diffcamp, and as I've already mentioned, the key idea behind diffcamp is to provide means for a highly scalable semantic equivalence analysis with a particular focus on large-scale programs written in C. And in this work, we also assume that two versions of the same program are compared. And in order to achieve high scalability in diffcamp, we translate both compared versions to the intermediate representation of LLVM, or LLVM-ER for short. And we follow these three key principles. That is, at first, we, whenever possible, simply compare all versions instructions by instruction, which makes sense since the compare versions are expected to be quite similar. And so by doing this, we can quickly show semantic equality of quite large parts of the code. However, this is of course not sufficient in many cases, so we also apply several cheap code transformations such as dead co-elimination, which bring the programs even closer together so that the instruction-to-instruction comparison can be used as often as possible. And finally, we use a set of built-in semantics preserving change patterns, which we know preserve semantics even though they fail the default instruction-to-instruction comparison. And these patterns can be anything from simple enum changes to code relocation and so on. And if each of them defines several things that are needed by the comparison, first, each pattern defines how to detect it in the first place and how to compare the semantics behind it. And then it also defines where the standard instruction-based comparison should continue after the pattern gets matched. And finally, it also defines what values should be considered semantically equal after the pattern is matched and applied. However, while this enables us to handle several semantics preserving changes, it does nothing for the safe but semantics altering changes we discussed, such as the security fixes and so on. So let us consider this motivational example. Where we can see the same simple change occurring in two completely different Linux kernel versions. And the change is an addition of the read once macro, which only prevents the compiler from merging or refetching memory reads. And theoretically, this is surely a semantics altering change, but practically it can be considered quite safe, which is why it would be beneficial to eliminate this change from the output of diffcamp so that it doesn't need to be manually inspected multiple times and so on. And now we move to our proposed solution, and to solve this problem, we propose to incorporate a new type of patterns, so-called custom change patterns, into the main diffcam analysis. And these patterns are custom-made and generic, and so they can handle the standard refactorings, which are not internally supported by built-in patterns already, but they can also handle the semantics altering changes we've just talked about. Okay, and we also propose to encode these patterns into LLVM-ER, which is beneficial to us not only because diffcam uses LLVM itself, but also because LLVM-ER represents functions as control flow graphs, which will be quite useful in a moment. And now we'll look at the pattern encoding. So we represent our patterns using parameterized control flow graphs, which we can understand as tuples with a control flow graph that is parameterized with 3 local variables and 3 types, and a set of input parameters of the control flow graph, so that the 3 variables and types can be mapped to the underlying code, and then also a set of outputs which defines which variables can be used after the CFG gets matched. And additionally, to construct a complete pattern, we define a custom code change pattern as another tuple that contains 2 of these parameterized control flow graphs, one for the older version of the compare program and the other one for the newer version. And then it also contains 2 mapping functions, imap and omap, which connect the input parameters and the output variables of the two parameterized CFGs for the old and new version together, which pretty much marks those parameters and output variables that must have the same semantics in both compare versions. And now this is a theoretical definition, and in practice we implement this using LLVM-ER. As previously mentioned, we can use the example of read once, which is a simple macro that changes how a variable is read, and we can encode this C pattern into LLVM-ER using 2 LLVM-ER functions, one for each parameterized control flow graph of the pattern. And these functions then correspond to the original C code. So we have a simple load on one side, on the left side, and then we also have a load that uses the read once macro or call in the LLVM function call in LLVM-ER on the other side. Of course, we do not want to specify concrete types and variables within the pattern, so we also use the parameterized CFGs to mark the types T and type T1 and the 0 variables as input parameters, and this enables us to bind these parameters and types to the specific variables and types during pattern matching itself. Similarly, we do the same for variables which we want to consider semantically equal after the pattern gets matched using the output sets of the parameterized CFGs, which is simply done using return instructions, as can be seen in this example. And finally, we also have to determine the mapping of inputs and outputs between the CFGs for the old and the new version. And we do this automatically based on the order of the returns and the input parameters, as can be seen in this picture. And with that, we have our patterns fully encoded into LLVM-ER, and the only thing still missing is the actual pattern matching algorithm. So let's look into that right now. For pattern matching, we propose to use an algorithm with 4 main steps. At first, we need to detect where the patterns reside in the main function control flow graphs. Then we need to ensure that the pattern inputs between both versions are semantically equivalent. And afterwards, we also have to ensure that we can notify diffcam about the values that have been matched to the pattern and that can be considered semantically equal, so the output values. And finally, we also need to tell diffcam which instructions exactly can be compared next, so which instructions follow the pattern itself. If we are looking closer into this pattern, we can see that, as we can see in this visualization, we can see that we have two separate control flow graphs that represent the same function in our compared program version. So it's an old function and a new function, which is simply just a version change between the same function. And in these, we need to find occurrences of the parameterized control flow graphs that are represented by the matching, by the pattern we want to match. And in theory, this is a standard subgraph isomorphism problem where we're trying to check if the parameterized control flow graph from the pattern, one for each compared version, right, for the old and the new version, are subgraphs of the corresponding function control flow graph. And while doing so directly is generally very expensive, we can greatly simplify this problem using the assumption that each pattern control flow graph has a single specific entry point from which we need to start matching all of the instructions. And we can use this, we can do this simply by following the control flow itself. And one thing to note here, that, however, is that at first we only find the subgraph matches for each compare version separately, and this helps us avoid additional computation costs that are related to input matching itself. So in particular, in this example, for example, we would first only match the highlighted load instruction, and this means that we still need to check that all input parameters defined in the pattern and the IMAP function are semantically equivalent. And to do so, we store both input and output matches for each of the parameterized control flow graphs. And for example, here we would map the type t to struct.t and the variable 0 to the variable 3. And we would also use the return instruction to map the output variable 1 to the variable 5 in the original function control flow graph. And afterwards, we can follow with the input parameter mapping, or we can check that the mapping corresponds correctly between the IMAP and the mapped parameters from the actual old and new functions. So we simply build a mapping of semantically equivalent variables during the main comparison, and afterwards we just check that the mapping corresponds to each other between the pattern and the functions themselves. And similarly, we did the same for the output mapping and the function omap to connect separately matched output values, and we remember these after resuming the main comparison so that the main comparison algorithm knows which values can be considered as semantically equal. And this brings us to how we continue the main comparison itself. And here we need to not only use the output mappings, but we also need to do two other things. We need to tell the algorithm which instructions got matched and don't need to be further compared. And we can do this simply by marking all instructions that got matched to instructions from the pattern CFGs. And the resulting control flow graph would look something like this, with the instructions corresponding to the read once pattern being grayed out, as you can see in this example. However, the algorithm also needs to know where to continue from. So, and we know that this can be a bit more complicated since a pattern may skip some unrelated instructions, for example, allocus and so on. For example, in this case, we can see that the pattern matched the alloca instruction here, but then skip the first get element pointer instructions. And needless to say, the get element pointer instruction still needs to be compared by the main algorithm, and after that, the remaining pattern instructions will be ignored, and the comparison will continue by comparing the following get element pointer instructions. And doing so finalizes the pattern matching process. And so now I'd like to talk a bit more about our experiments. We've conducted two experiments. First of all, we've tried to demonstrate the practical usability of our approach by applying 5 repetitive custom patterns to several recent versions of the RHEL kernel. that is the kernel of Red Hat Enterprise Linux. And first, we identified 5 patterns of changes which repeat across versions, and while they alter semantics, they are also quite safe to be done. So it makes sense to remove them from the output of different instructions, functions. And these can include the read once pattern and the corresponding write once pattern that is basically pretty much the same but for memory writes, and other patterns that generally modify compiler behavior. For those that are interested, we provide a complete description in the first appendix of our paper. And after identifying all of these patterns, all 5 patterns, we ran 2 semantic comparisons of 4 pairs of recent versions of RHEL 8 and a single pair of versions of RHEL 7, one with and the other without custom patterns. And in each comparison, we compared all functions from the kernel application binary information, or KBI, which is pretty much a list of functions that is guaranteed to remain stable across minor releases of RHEL. And the results are shown in this table, and we can see the functions that are identified as semantically different with and without the usage of custom patterns. And the table also shows that by using only 5 patterns, we were able to in total remove 19 differences in functions, and that is there's almost 4 differences per each pattern. And while this may at first glance seem like a relatively small number, it may still translate to a substantial reduction in the amount of human effort that is needed to review all differences, since the affected functions are called from numerous places around the code base. And finally, I would also like to highlight that each pattern was successfully applied in at least 2 different versions of the RHEL kernel, which also suggests that our pattern representation is generic enough so that it can be defined so that each pattern can be defined just once and then used across multiple versions of the same project. And this, of course, could translate to even more of a substantial reduction in human work required to review the function differences. And finally, we also demonstrated our pattern matching method maintains the high scalability required by diffcamp, and we did so similarly to our first experiment, only this time we applied 24 patterns, with the original 5 being there, as well as 19 patterns from our regression tests, and we measured the runtime as an average of runs of 5 runs. And before we see the results, I'd like to note that though most of these patterns never matched, the algorithm itself still had to try to find a match, so it still had to run itself. And now the results can be seen highlighted in this table, and we can see that for all versions the runtime was the same or even slightly shorter when running than without patterns, which could have been caused by the reduction of time needed to find occurrences for difference localization and other things that need to be done for each difference that is detected. And either way, this shows that our matching algorithm is efficient enough, even for the use with diffcamp, where high scalability is key. And in conclusion, we proposed a way to encode custom patterns of changes and a way to detect the encoding patterns during semantic analysis of semantic equivalence performed by the diffcamp framework. And in our experiments, we also showed that the approach is able to eliminate false positives as intended, and that the pattern matching method is highly scalable and can be applied to large code bases, such as, for example, the kernel of RHEL. And for future work, we would like to address the need for manual definition of our patterns via LLVMER, possibly by automatically inferring patterns from analyzed code it themselves. And with that said, I would like to once again thank you and thank all my colleagues in Brno University of Technology and Red Hat, and I wish you a great rest of your day.